Hello everyone, I am Daniel and I will be working with Sean and Michael to present on constrained optimization. As you likely learned in the previous lessons, a quadratic form is essentially a multivariate equation in the form of a matrix. What this means is that for a matrix A, when thought about as a quadratic, the matrix will take upon some of the properties of the quadratic, allowing certain operations, one of which being constrained optimization, to be performed upon it. All of you are likely familiar with optimization in reference to maximizing and minimizing values, and, as the name suggests, at its base level, constrained optimization is just finding maximum and minimum values of a given equation under given constraints in order to find an optimal solution to a problem. In the real world, constrained optimization will be seen in the same places that normal optimization is seen, such as in economics when maximizing revenue and minimizing costs, and also in architecture as well as engineering where finding optimal size and amount of a given material is necessary.
The first important theorem for optimizing constrained quadratic forms is Theorem 6. Theorem 6 involves a quadratic form Q of t is equal to x transpose AX with symmetric matrix A. To find the minimum and maximum values of Q, where x must be a unit vector, little m and big M respectively, we just have to find the eigenvalues of A. It turns out, the largest eigenvalue of A, denoted by lambda 1, will be the maximum of the quadratic, and the minimum will be the smallest eigenvalue. After you've found the minimum and maximum of a quadratic form, questions will often ask you to find a unit eigenvector u1 corresponding to the maximum. Remember that vector u1 corresponds to the maximum value, lambda 1. Remember this because it comes in handy later on. You may recall from earlier chapters that you can set the quantity of A minus lambda I times x to 0 in order to find the eigenvectors corresponding to lambda. Simply apply this to the maximum to find u1. In the case where more than one linearly independent eigenvector corresponds to the maximum, u1 can be any unit vector that is a linear combination of the multiple corresponding eigenvectors. Let's look at an example. To find Q subject to x transpose x equal to 1, as the following with eigenvalues 9 and negative 3. Find the maximum value of Q and the unit eigenvector u1 that corresponds to it. First, let's find A. By the process explained in the introduction, we know that the value in the top left is 7, middle is 1, and the bottom right is 7. Since the coefficient of the x1, x2 term is negative 8, we split that value between the top middle and the left middle positions to get negative 4 in each. The coefficient of the x1, x3 term is negative 4, so we split that value between the top right and bottom left positions to get negative 2 in each. Lastly, the coefficient of the x2, x3 term is negative 8, so we split that value between the right middle and bottom middle positions to get negative 4 in each. Now that we have A and know that it is symmetrical, Theorem 6 tells us that the highest eigenvalue 9 is the maximum. To find the unit eigenvector corresponding to 9, we solve the following matrix equation for x. We start by making our augmented matrix, simplify, reduce to reduced row echelon form, and find our eigenvectors. For this problem, two linearly independent eigenvectors correspond to 9. That means u1 is any unit vector that is a linear combination of the two vectors. To state our answer formally, the maximum value of Q under the given constraints is 9, and the unit eigenvector u1 corresponding to 9 is any unit vector that is a linear combination of the vectors negative 1, 0, 1 and negative 2, 1, 0.
Now we will do Theorem 7. Since we can see the eigenvalues in the diagonals of the D matrix, we can use that to find the maximum and minimum values. However, the maximum and minimum may change depending on the constraints. Let the constraints be x transpose times x equals 1 and x transpose times u sub 1 equals 0. Remember that the first eigenvalue would be greater than the second, and the second will be greater than the third, and so on for A. So that means that the second eigenvalue will be the maximum instead of the first eigenvalue, because it's x transpose times the u sub 1, which corresponds with the first eigenvalue. Let's consider the equation 11 times x sub 1 squared plus 6 times x sub 2 squared plus 2 times x sub 3 squared. And this is constrained by x transpose times u sub 1 equals 0 and x sub 2 squared plus x sub 3 squared equaling 1. Since we know that x transpose times u sub 1 equals 0, this implies that x sub 1 is equal to 0 as well. So all we have to do is just create an equation without the first term. We can create the inequality 6 times x sub 2 squared plus 6 times x sub 3 squared. And we could just do some algebraic manipulation to find that the equation is less than or equal to 6, meaning that 6 is the largest maximum there is. So therefore, the second eigenvalue is actually the maximum, since the first one is gone.
Theorem 8 is able to give all eigenvalues of a matrix A by means of Theorem 7 and Theorem 6. Because it is given that A is symmetric with orthogonal diagonalization, A equals PDP inverse, where its eigenvalues 1, 2, and onwards are oriented in a decreasing order, and the columns of A are eigenvectors, and for the values of K of 2 and onwards, the maximum value of x transposed AX has the constraints of x transposed x equals 1, x transposed eigenvector 1 equals 0, and x transposed every eigenvalue onwards equals 0. Essentially, what Theorem 8 does is give constraints for a given matrix under the circumstances that A is symmetric and orthogonally diagonalized. For instance, if we have the equation 12x squared plus 72y squared is greater than or equal to 144, which can be rewritten as 12x sub 1 squared plus 2x sub 2 squared equals 1, because x sub 1 is equal to 1 over 12x and x sub 2 is equal to 1/2 x. The constraint x transposed x equals 1 is given, so q of x is equal to 24x sub 1 x sub 2, meaning that A is the matrix 0, 12, 12, 0. And by this we know that the eigenvalues of A are plus or minus 12, and the maximum value of the equation is 12, according to Theorem 8, where the eigenvector is 1, 1.
Apply this knowledge to real-life scenarios as well, such as economics, where you may need to allocate some resources. Let's go over some definitions. The constraint curve contains the feasible set. This means that anything within or on the curve is within cost boundaries, and that there are enough of available resources to perform such a task. Another term is the indifference curve, which is found by the utility function. The indifference curve shows public satisfaction, and anything on the curve will make this public satisfied by allocating their money towards that project. This problem. A city is repairing the parks and roads and needs to find the optimal division of costs. The variable x refers to the roads, and the variable y refers to the parks. We can see the equations 4x squared plus 9y squared is less than or equal to 36. This is the constraint curve. We can make the oval into x over 3 all squared plus y over 2 all squared equals 1. At first you might be thinking, why is it equal and not less than or equal to? Well, that's because if we want to make the most optimal use of costs, we have to use all the resources. Anything on the curve is a use of all resources. So, we can now continue forward and look at the utility function, which is x times y. Where the indifference curve and constraint curve meet at one point is the optimal use of spending. Though the indifference curve is very important, we don't really need it to find the calculation that we're looking for. But knowing this, we can see that x times y equals 3 will meet the constraint curve at one point. That's the point that we want. So the first step is to replace x's and y's. We can do that by doing x equals 3x1 and y equals 2x2. So we're basically putting x's and y's into x1s and x2s. Now we can plug this into the utility function, giving us 6 times x1 times x2. This is now our quadratic function that we learned earlier. And we can maximize this with q of x equals 6x1 times x2, and the matrix is 0, 3, 3, 0. And the eigenvalues are 3 and -3. I didn't put the eigenvalue calculations on the screen because I'm sure we know how to do that already. But nevertheless, we can see that 3 is the largest eigenvalue. Therefore, we'll need to find the eigenvector associated with it. Again, through calculations, we can find that it's 1 over radical 2 comma 1 over radical 2. However, we left this in the variables x1 and x2, so we need to put this back into the original variables. which will give us 3 over radical 2 for the roads and 2 over radical 2 for the park.
As of now, we have reached the end of our presentation. I just quickly wanted to recap a couple of points. For a quadratic form, you will be given a form of q of x is equal to a times x sub 1 squared plus b times x sub 2 squared plus c times x sub 3 squared for a symmetric matrix A. The coefficients of the variables happen to be eigenvalues of the A matrix for q of x is equal to x transposed times A times x, and the largest eigenvalue is the maximum, while the smallest eigenvalue is the minimum. In addition, we found that if x transposed times u sub n is equal to 0, then eigenvalue sub n is not the maximum if there is some eigenvalue greater than 0. Thank you. And don't forget to like, comment, and subscribe.